Hi, I'm Ahmed Dawood, and in this session we will see polynomial regression. So we have started from the linear regression, in which the linear model involved to predict some continuous target variable. We have seen linear regression involving just one independent variable, then the extension of linear regression in the form of multiple regression, in which there are multiple independent variables are involved. We have seen how we can train linear models or linear regression. Theoretically, we have seen create a descent and a normal equation, and practically we have implemented the Scikit-Learn linear regression. We have also seen the evaluation metrics that can be used to evaluate the regression models. Now, here the problem is till now we have understand and learn the linear models. Okay, as you know, regression means that in statistics regression represent the relationship. Okay, so linear regression means we are trying to find linear relations or linear relation between the independent variables and dependent variable. But the problem is in real world scenario, the data is not so linear, and the real world scenarios are not so simple that linear model can fit the and or you can say they capture the pattern from the data. Okay, sometimes data is about sometime like most of the times data that we have is not so linear. It has some sort of non-linearity in it. Okay, so if the data has non-linearity, so we want such a model that is non-linear and can capture the patterns from the data so that we can predict for the future. So here we have an example that we moved on the polynomial regression that can help us to implement non-linearity. Okay, so here we have data set in which six data points we have. These are the, if I will zoom in. Okay, so just six data points, and you can see here in the form of scatter plot, these six data points are here. When we have implemented a linear model, or you can say linear regression, on that data set, you have seen that there is a lot of gap between the predicted values and true values. Then we have seen the score of that model according to this data set is 62%. Here the linear model has accuracy of 62%, you can say, or score of 62%, and mean square error, which is here 6.18. And you know, mean square error is average of sum of squared errors. Now you can say on average, each true value or each predicted value has a 6.18 points away from the each true value. Okay, you can say like your prediction here that you're predicting is 6.18 away from your true values. So you can see there are a lot of gap between true values and predictions. Okay, when we have implemented a non-linear model here, if I will show you here, you can see here I have implemented a model that is not linear. It has a shape and clearly showing that it is non-linear. So here you can see when I have calculated the score, you can also see from this graph and plot that there is a very less difference between the true values and the predicted values. Just in the case of this point, there is a some difference between the true value and predicted value. Overall, there is very less, and you can also see from mean square error here is 1.42. You can say your predicted values on average are 1.42 away from your true values, and your model score is also 91.4% here. You have seen that when you have the data which is non-linear, you cannot capture the patterns from the data by using linear model. You have to use some non-linear model if you want to generalize your data, or if you want to find the relation between your independent variables with the dependent variable. So here we will see polynomial regression. For that, to implement non-linearity in the regression. So first of all, what is polynomial? In mathematics, a polynomial is an expression consisting of variables and coefficients that involves the operation of subtraction, addition, multiplication, and this is important, non-negative integer exponentiation of variables. If I will write this one, non-negative integer exponentiation of variables. Okay, here we have variables that have some powers. Okay, so like here there is expression x square is plus 4x minus 7, and here the variable has some power. Okay, of course here the single variable is involved, just one variable x is involved here. So x square plus 4x minus 7, and we can say this is degree 2 polynomial expression. Okay, the highest power involved in the expression represent the degree this expression have. Like in this case, this is also a polynomial expression because there is some exponentiation of variables. So x cube plus 2xyz square minus yz plus 1. There are three variables involved here, and the highest power in this expression is 3. So that's why this is degree 3 polynomial expression. You got an idea in which we have some exponentiation of variable. The expressions we have, we usually call it as polynomial expression. Now, what is polynomial regression? In the same way that we have defined linear regression, you can describe the polynomial regression. Regression means you are in statistics. Regression is uh, represent the relationship. Okay, you are trying to find relationship, then you can say that you are doing regression. Okay, so polynomial regression is mean that you are trying to find non-linear relation between the variables. Okay, so here sometimes we have data that is not so linear, so we applied our linear model and it gives a very less score like we have discussed in the example here. Then we apply some non-linear models, and we try to find out that how good our non-linear models are here to represent these data. So if our non-linear model will give us a good score or less error, then we can say our data is non-linear here. That's why we should implement some non-linear model here instead of some linear model. Okay, so here we are trying to find non-linear relation between the independent variables and the dependent variables. So that's why we call it as polynomial regression. So we have understand what is polynomial regression actually. So now we will jump towards how we can implement that and how it usually represented here. Okay, so it's very similar to the linear regression, just the powers involved in the equations. Okay, simply when we have linear regression, we have our equation like y cap is equal to theta 0 plus theta 1 x1 plus theta 2 x2 up to so on theta n xn. When we have n number of variables, or you can say features, and here you can say the highest power involved here is just 1. So that's why we call it as degree 1. Okay, so that's why we can call it it's degree 1, and this is the reason that that's why it is linear. There is no power. Okay, as I told you in the last session that we can prove the multi-dimensional model by mathematics that it is linear model, and the reason is that because there is no power involved in the expression or in the equation of model. So here there are some examples here. I will explain one by one. Like when we have single variable, just one independent variable, and the equation will be equation of model will be like that. Y cap is equal theta 0 plus theta 1 x. Okay. So this type of equation we call as there is highest power is 1, so we call that this is degree 1. Okay, this is degree 1 expression, you can say. If we want to represent degree 2, then the equation will be like that: y cap theta 0 plus theta 1 x1 theta 2 x1 square. Okay, if we want to want such a model equation that has degree 3, so we can say y cap is equal to theta 0 plus theta 1 x1 theta 2 x1 square plus theta 3 x1 cube. As we are increasing our degrees, our parameters are increasing. Like here in the first case, we have just two parameters. Here we have three parameters that we have to find during our training. There are four parameters are involved. And you can see here, there is just one single variable in each case. Okay, just we are adding some squared uh, variables as a separate features. When we have two variables involved, the same in the same way the equation can be extended here. Okay, so like here y if I will show you here, y cap is equal to theta 0 plus theta 1 x1 plus theta 2 x2. It will be a degree 1 equation of model. If you want to see degree 2, then theta 0 plus theta 1 x1 theta 2 x1 square theta 3 x2 theta 4 x2 square. In the same way, degree 3, theta 0 plus theta 1 x1 theta 2 x1 square theta 3 x1 cube theta 4 x2 theta 5 x2 square and theta 6 x2 cube. Here there are three parameters are involved: theta 0 1 2. Here are total five parameters: theta 0 1 2 3 4, and here are seven parameters: theta 0 1 2 3 4 5 6. Okay, and sometimes we also have can see the equations like that in which their interactions are also involved. Okay, I will explain in a while that what I am saying here. Like here, like here, if I will extend this equation, sometimes the expressions are also involved. If I will, okay, so like y cap is equal to theta 0 plus theta 1 x1 plus theta 2 x1 x2. Okay, the product of both variables plus theta 3 x2. Sometimes we also have interactions in our equation of model. Okay, so in which we have some powers, then we can say that our model, you can see, as we are increasing our degree of equation, our the parameters of to find the parameters, or you can say that the parameters involved in the equation are increasing. As parameters are increasing, your model is becoming complex, or you can say becoming more powerful. Like here in this case, degree 1 model, if one variable involved, degree 1 power model will be less powerful as compared to degree 2, and degree 2 model will be less powerful as compared to degree 3. Okay, as the degree is increasing, the powers are increasing in the equation of model. Your complexity of your model, or you can say your power of your model, is increasing. Okay, now there is a the situation that we have to see during our real time problems, that what how complex our data set is, how much complexity between our independent variables, and or how much complex relation between our independent variables and dependent variables. According to the complexity of their relation, we have to implement our model, or we have to implement the model's complexity. We have to that type of implement that type of model that can sync the complexity of the data set, or that can capture the patterns from the complex data set. Okay, we of course we will implement multiple models by the increasing model, like a degree 2 model, degree 3 model, degree 4, degree 5, degree 6, and which will give us a good accuracy. We can implement that, and we can say that our data is so much complex, so that we have to use this type of this degree model. Okay, so here, as our degree is increasing, our complexity of model is goes upward. Okay, goes upward, or you can say our model become more powerful, and also complexity of data set. Okay, so as our we have to find the complexity of data set, how much complex relation between independent variables and dependent variable of our data set have. So according to their complexity, we have to implement our model. Okay. So till now we have to understand polynomial regression theoretically. Just these some powers involved in the equation of model, and the model become nonlinear. Okay, we have seen, and the same process followed in the training phase, like we did in the case of linear regression. Our sum of squared error, we used sum of square error usually in the training process, and we try to minimize sum of square error to get some optimal parameters. Okay, or you can say in this way, if I will write more precisely, we usually try to minimize our sum of square error, which is in the form of these parameters. Okay, and here sum of square error will be, sum of square error we usually write in this way, all the points 0 to n or 1 to n, or y which will be true value, and y will be prediction. Okay, as our what type of model we are using here, we will pass the equation of that uh, polynomial model. Okay, so our training process will be the similar. If we there are multiple parameters, like 10 parameters involved in the equation, then during this the training process, we have to find 10 optimal parameters. Okay, so we have understand till now polynomial regression. What exactly is polynomial regression theoretically? Now, how we can implement it? Okay, so implementation is very simple, and we can implement it by using Scikit-Learn linear regression, and I will show you how we can implement that. First, we will see here how we can implement, and how what process we will follow, and after that we will jump towards the Jupyter notebook. Okay. So implementation by Scikit-Learn. Let's say we have this equation y is equal theta 0 plus theta 1 x. Okay, when we have just one variable, so we have equation like that. Okay, so in the case of polynomial, like a degree 2 polynomial, if like we have implemented here in case of our example, like this one. Okay, this model will have equation like this blue one will have the equation like that, or y cap is equal to theta 0 plus theta 1 x. Okay, yeah, as there is just one independent variable, so that's why there is just one coefficient here, and one intercept involved here. So this model will have, as it is a degree 2 polynomial, degree 2, this one is degree 2. So the equation of that model will be like that, theta 0 plus theta 1 x plus theta 2 x square. Okay, this model will have equation like that. Okay, so this model will have equation like that. Okay, now we have just one independent variable x, and there is but we have two coefficient, because one for the uh, x and one for the x square. Okay, so if we can replace, or we can mark as x as a separate variable, separate feature, and x square as separate feature x1, like we have given the name to this equation like x 1 is equal to x, and x2 is equal to x square. We make them some separate features, and we have replaced our equation like in this way. O y cap theta 0 plus theta 1 x1 plus theta 2 x2. Seems like there are two features involved here. That's why we are finding here two coefficients and one intercept. Okay, we just has replaced the names here. Okay, we have uh, like you can say we suppose that these are the as a separate features. Okay, x is separate feature and x square is a separate feature. Now we have done that. Now we can simply use the linear model. Let's say uh, before we have just this data set in which we have x here and one will be y, if we can say here y. Okay. Now we have in the case of linear model, but in the case of polynomial model, we have x1 and x2. Like x1 is x and x2 is x square. Okay, if we will pass this as a data set to our linear model, linear regression that we have learned till now, of the provided by the Scikit-Learn, and we will pass the x and x square as independent features and y as a dependent feature, and the linear model, linear regression by Scikit-Learn will calculate the equation or parameter values, which will be y cap is equal to theta 0 plus theta 1 x1 plus theta 2 x2. Okay. Now you can see we have to we can implement the same linear regression by a Scikit-Learn. Just before that, we will convert our data into the that form. Okay, according to our degree of equation. Okay, so there is another the class or you can say module we will use for that purpose to convert our data set into required degree, which will be a scale and polynomial features. Okay, we will pass our x data set that here, and then we will mention that our degree, we want such a data set that has a degree is equal to 2. Then it will convert this data set into this data set in which we have this 2 into this, in which we have x and x square, two features instead of two. Then we can use simple linear regression model. Okay, you can see that we instead of just implementing or directly implementing some polynomial regression model, we first convert our data into some polynomial features. Then we use that polynomial features in the same way that we have used the linear regression. We assume that these polynomial features are the real features of our data set, and we pass these as a independent variables to our linear model or linear regression, and then we train our model and we can get our results and parameter values. Okay, you got an idea that we can use the same class Scikit-Learn or linear regression by Scikit-Learn. So now we will move towards the code, how we can implement that. So if I will make it okay, now it will be the uh, usual libraries I have imported here. Pandas, Scikit-Learn. From the Scikit-Learn, will import the linear model, Seaborn to for the some visualization, warnings, load filter warnings to ignore the warning, and matplotlib as by a plot, again to plot if some plots, if we require that, we can use that. So there is one the something new for you is today's from sklearn pre-processing import polynomial features. Okay, this one, this class polynomial features, it's exactly the same that we have seen now in the notepad, that to convert our original data set into some polynomial features so that we can use our linear model or linear regression. Okay, so linear model dot linear regression, if I will show you here. Yeah, this one, linear model dot linear regression, so that we can use that. So we will we can use that polynomial features class. So before going towards the implementation of the same data set that I have shown you in the pad, I will use here, and I will implement some the same data set I will use here. and I will try to implement polynomial regression here. Okay, and show you how we can do implementation of polynomial regression. So before going towards, we should learn what is polynomial features and how we can use that. So if we will go to the documentation of that polynomial features, okay, here you can see here polynomial regression, polynomial features is a class by Scikit-Learn. It is for us to generate a new feature matrix consisting of all polynomial combination of the features with degree less than or equal to the specified degree. Okay, if we have mentioned that degree is equal to, then it will like here they have also given an example. For example, if an input sample is two dimensional, let's say we have two columns in our data set A and B, and of the form like A and B, and then we have used the degree 2 polynomial features, then it will result into a data set that have 1, 2, 3, 4, 5, 6 columns. Okay, I will explain you. The first column, which is here they have mentioned as 1, the whole column will have 1 as values. Okay, maybe you have a question in your mind, why the whole column is 1 here. This is for the bias term. So here we don't need to use that, but maybe or in some models we usually use that bias terms, and where the whole column involved as a 1. So for now ignore that. So we have it can generate these 6 columns: A, B, A square, the interaction of A and B, which we can say AB, then the B square. Okay, total 6 columns it can generate here. Now we can see the parameters here. The parameters are degree, interaction only, include bias, order. Okay, for us to consider is just the important one is include bias and degree, and order is of course not uh, here to like explain you. It's for the array, or in some cases when we have a dense data set. So it's up to us that we can use order is equal to C and F. By default they have specified as C, so we don't need to change that parameter. So degree, which degree we want to in which degree we want to convert our data, we can specify here in that parameter. Okay, we can also specify as a value that we want some like a degree is equal to 2 here, 2, or degree is equal to 3, that number of we want. If we have to specify like if we have degree is equal to 2 or degree is equal to 3, we can specify here we want such a data which has features in which the degree of 2 is involved, degrees, or you can say degree. If we have specified degree 3, then degree 3 and less than 3 are involved here. Okay, so if we will pass a tuple, like in which we can also specify that minimum degree should be in that data set should be this one, and maximum this one. Okay, let's say if you have a data set here x. Okay, let's say just x variable here you have, and you want to convert it into like you want uh, x raised to the power 4, x raised to the power 5, x raised to the power 6. Okay, you can pass a tuple here, which will be minimum degree will be 4, like a 3, and maximum that we have 3, 4, 5. Maximum will be 5. Okay, so 3 comma 5 you can pass here, and it will convert your data, your x into x raised to the power 3, x raised to the power 4, x raised to the power 5. Okay, so here include bytes before going to the interaction. Only include bytes is like here we are not interested in the ones, the whole column containing ones. So we can specify, or we can uh, specify the this parameter include bytes is equal to false. By default it is true, we can specify it is equal to false. Now what is interaction only? Like I have shown you, like sometimes we have this type of AB, like just the interactions. So if we are interested in just interactions of the variables, we can specify here interaction only is equal to true. Okay, like if you will go in the user guide of that, polynomial features, you will see here an example like this one. If you have data set like that, like this is data set in which you have three columns and three rows. Okay, you can consider that you have three columns x1, x2, x3, and you want to convert it into degree is equal to 3 and interaction only is equal to true. You have made that interaction is only is equal to true. Then you can go here and you can see your x will be converted into x1, x2, x3. You have originally it will be converted into 1 as your base term is by default true. So x1, x2, x3 feature x1, x2, the product of x1 and x2, the product of x1, x3, the product of x2, x3, the product of x1, x2, x3. Total 1, 2, 3, 4, 5, 6, 7, 8. 8 features you will get. Okay. So if you will not specify that interaction only, which is by default equal to false, like here, if you have two columns, and you want to convert it into according to degree is equal to 2, how it will be converted like x1 and x2 if you have originally, you will convert it into 1 as a base term, x1, x2, x1 square, then the product of x1, x2, and the x2 square. You will total have 1, 2, 3, 4, 5, 6, 7 features in the output data set. Okay, come back here. So interaction only you have understand if you are interested in just interactions. So in our case, we are not going to use that parameter also. We will just use degree parameter and include wise. And order, here they have mentioned that order of output array in the dense case, F order is too faster to compute but may slow down subsequent estimators. So we can get the same result if we can use F also. But default parameter is C, uh, we are done or we can get our result with that parameter also. So there are some attributes. These are the like not so much useful, like powers. I will show you in a code that how we can use powers attribute and what it can give you as a result. Okay, all the attributes I will show you here. So before going to use it in this code, I will just give you an idea how we can use polynomial features here. Like here, let's say we have a input variable data set x1. Okay, this whole data set we have as input, and here we have a polynomial features class that here I have imported from Scikit-Learn pre-processing. Here I have mentioned degree is equal to 2. That I am saying that the data set that I will pass, just convert it into according to degree is equal to 2 features. Okay. So it will convert like p dot fit transform. It will convert my features like the first column will be just once in the whole column. Second will be 5 x column. This column is x. This one, this one, this one, this one. Okay. So x, y, x square, x into y. Here you can see if you will multiply 70 into 1, you will get this one. Okay. And the last column here is representing y square. Okay, in the same way, like here they have mentioned, like here, 1, the whole column containing ones, this will be x, y, x square, x, y, y square. This number of columns you have here. Now, I will show you the attribute here that you have learned, p dot powers, okay, that you have seen here, powers attribute here, this one. Okay, you can use that if you want to see the column powers or feature powers here that you have generated here. You want to see which column is representing which variable and which power. You can see here the first column. This one is first column is representing that the power of here. This one is your x variable and y variable. So in the same way, they have there is the first one dimensional array is representing this. This is first is x and this is y. Okay, so this whole one dimensional array is representing the power that the first column have. So it has x raised to the power 0, y raised to the power 0. So it is uh, of course it is equal to 1. So second column is x have a power 1 and y is equal to 0, y have power 0. So here you can see the second column is representing x, third column is representing y, fourth column is representing x square, fifth column is representing x into y, and last column is representing y square. Okay, in this way you can use this attribute to see the powers of the each column. Now, if you will make include bias is equal to false, you will have the same data set except that column, the first column. Here you can see 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and this one 6. So we have 5 columns here. So if you will make degree is equal to 3, now you will have this number of how many these are 1, 2, 3, 4, 5. Yes, you will have 10, uh, 10. You can see 10 columns here. Okay. So you can see each column like the first column is X. First column is a byster. Yeah, first column is byster. Second column is X. Third column is Y. Fourth column is X square. Then the XY, Y square, X cube, X square Y. This is interaction. X Y square. Last column representing Y cube. Okay. So how many columns it generate this polynomial features? You can have this formula x plus d, oh sorry, n plus d. N is number of what is and represent number of features, and d is degree. Like here the number of features two features, and degree is 3. So n plus 2 like 2 plus 3 5. 5 factorial divided by d is 3. 5 factorial divided by 3 factorial 2 factorial. When you will calculate that, you will get a result of 10. And you here you can see it has generated 10 columns. Okay. Now you will get the same result if you will change the order. By default, it is using the C. Order is equal to C. You will use F. The same result you will get, and you can check it by using powers. Okay, what these some attributes you can use that, like how many number of input features you have, like 2 features. There is n features in the same result. It will give you the same functions both attributes have. What are the names that you of your features that you have used for input x y? How many features you have generated as output? Total 10 features. Okay, you can use these attributes accordingly. So if you will here mention include bias is equal to false and you are interested in just interaction only, there and degree is equal to 2. So you have just two variables. This will be x, this will be y, and this will be xy. And you can see that also x, x, y. The second column is y, and last one is x, y. Okay, so yeah, if you have here interaction only is by default is equal to false, so no need to use that one. I will remove this one. If you have just one variable, okay, like just one column, and in this code in this example or problem that we are going to implement, or we are going to use the polynomial regression here. We have this data set x and y, x as independent variable and y as a dependent variable. So we will use just one variable here, x as independent variable, or we will convert this x into some polynomial features. So originally we will use in that example of code just one variable as an independent variable. So the same, if you will use just one variable like here uh, and mention a degree is equal to 4 and include bias is equal to false, and you will use just one variable, it will generate here x raised to the power 1, or you can say x, this column representing x square, this column is representing x cube, this last column is representing x raised to the power 4. Here you can see from also by the powers. Okay, and there is no interaction because we are using just one variable here. Okay, now moving on towards the today's till now we have seen what is polynomial regression, and theoretically we have used the concept. Practically we have till now we have seen how we can use polynomial features provided by sklearn. It's a technical part. Now we will move on towards the part of implementation of polynomial regression, in which we will have theoretically we have discussed that we will convert our independent features into some polynomial features. Then we will use the same linear regression model. Okay, in this code, we will use the linear model first on the same data set. Then we will use polynomial model with the degree 2, then with degree 3, then degree 4, degree 6, and we will see the comparison as degree is increasing. Our model is becoming more powerful, and our error is going to decrease, and our model will getting the score as the degree is increasing. So here you will see we will just split our data set into x and y. Okay, so here is x, we have y here. So here you when you will plot your x on the x-axis and y on the y-axis, you will have just this type of like this type of scatter points here. Okay, you can see here there is no exact linear relation between the x and y here. Now here I have used the linear model dot linear regression provided by the sklearn linear models. So I'm using that, and here fitting or doing training on the x and y. X has independent features and y has independent feature. So now here I am going to predict by till now our linear model has been trained here, linear regressor. So I am using that linear regressor to predict the values of x. So these are the predictions I have here, and when I have placed the prediction against the true values in the data set, you can see these are our true values, and here are some prediction, and you can also see there are a lot of difference between the true values and predictions here. When you will see in the form of plot, you can see here this is our linear regressor and these are our original points. Okay, and on the y-axis you can see these are the true value, and according to prediction the value is here like 18. Okay, prediction is 18 but our true value is 15. The score of that linear regressor is 62% or 0.62, and the error here is mean square error is 6.18. Okay, now I am going to implement polynomial regression with the degree is equal to the bias is equal to false, because we don't need to have such a bias here, because we already have in the linear regression we already have interceptor. So poly is equal polynomial features degree to include bias here. So poly dot fit transform. I am going to transform my x, just one column in the x we have. If I will show you this column into polynomial features of degree 2, I am going to convert that column into polynomial features of degree 2. So you will see here in this way I am going to convert it. So now this first column is x and the second column is x square. When I have convert that numpy array into the pandas data frame, you can see here this is x column, this is x square column. Now I will use these two columns as a separate features into or as independent features uh, to train my linear model. Okay, so automatically when we pass our polynomial features to the linear model, our overall linear model will become a polynomial model. So here I am going to use a linear model, the same linear regression here, and to train my polynomial model. You can see because I am passing polynomial features here. Here you can see I have trained my model. Now I am going to here are my predictions are also saved in that. So when I will plot the graph of that, you can see here. Okay, now that plot I have shown you in the theoretical part. Here you can see the plot is non-linear here. You have seen that we have implemented the same linear regression here, but our plot is non-linear because we have fed here the non-linear or polynomial features here. Okay, and you now here instead of just one uh, coefficient, we will have two coefficients here. If I will show you here, see coefficients in the same like I have also here I have printed here, but you can see here also we have two coefficients instead of one. But the above model have just one coefficient and one intercept. This model have two coefficient and one intercept. You can see here the score of that model is 91% and the mean square error is 1.42. If we will say our parameters here, m1 is 8.4, m2 is minus 3.5, and intercept is 12.1. Okay, if we will uh, output our data frame in which we have our polynomial feature x original one, x square which is polynomial feature, y true values, and y prediction predicted by our model. And you can see here very close to our predictions. Okay, our true values, our predictions are. Now here I have implemented different models. I will also show you here all the implementation of all models. Now you can see here as our model, this is linear model in which we have just one parameter. This is a polynomial model with degree 2. So there are the equation will be like that m2 x square plus m1 x plus c. Here this model is degree 3 model which is the equation like that y cap is equal to m3 x cube. If I will zoom that for you to get an idea, here you can see. Okay, so this model have equation y cap is equal to m3 x cube plus m2 x square plus m1 x plus c, and the last one is polynomial with the degree is equal to 3 6. And you can see so much model become powerful that it has uh, extracted all the patterns, or you can say it is perfectly uh, it has perfectly captured the pattern of the data. You can see it is exact only all on all the points of the data. And you can see in that case we have very less like a 0 point uh, like here you can see 7.4 into 10 raised to the power minus 24, like approximately we have zero error here. In the case of that model, degree is equal to 6. And as our degree is increasing, our error is going to decrease. Like in the case of linear, we have 6.18 error. In the case of degree 2, we have 1.4 error. In the case of degree 3, we have 0.6. And in the case of degree 6, we have approximately 0 error. Okay, so we will implement all of that. So this is the polynomial features. I have converted my uh, x into polynomial features, x, x square, x cube. Now I have three features here. So accordingly, we have three coefficients here. Okay, I am going to train my linear model. Automatically, it will become polynomial model. These are my predictions. This is the my model that we have. You can say this is a polynomial model, non-linear model with the degree is equal to 3. Degree 3, or you can say the equation of that model have degree 3 expression. Okay, you can say here. The score of that model is 96%. You can say as we have increased our degree, the power of our, capturing the pattern of our model is increased. Okay, become more flexible, more powerful our model is. That's why it has reduced the error, and 96% our score become here and a reduced error to 0.6 here. Okay, last model has 1.2, degree 2 model has 1.2, 1.4, sorry. This degree 3 model has 0.6. And here we have three coefficients and one intercept here. And you can see the predictions are also become as degrees going on increase, our predictions are becoming closer to our true values. Now this one is degree 6. I have implemented here. It is perfectly capture all the points here. Okay. So you can see the power of our model is increased so much by increasing the degree of the equation. Okay, of course, when we make our model, like model has six parameters. Okay, now it can use six parameters against the six features to get a result for the against the true value, it can get a result that will be, of course, equal to, like here you will see, in the case of 6, our prediction is 15, true value is 15. Our prediction is 17, true value is 17. Exactly, it has captured all the points here. Okay, as our model become, and you can see here, degree 6 have here 1, 2, 3, 4, 5, 6, 6 coefficients and 1 intercept. 7 parameters it has here. Okay, and 100% accuracy and zero error here we have. Here now, if you will do a comparison of score, like here in the case of linear regression, we have 62% score. Then in the case of degree 2, our score is increased 91%. Then in the case of degree 3, become 96%. In the case of degree 6, it become 100%. And as you can also see the score error comparison. In the same way, you can see the comparison of your predictions. Here in the case of linear model, your prediction like true value is 15, but predicted value is 18.38. But in the case of degree 6, your prediction is also 50. Okay. Now you got an idea. We can also implement non-linear model, and we should implement non-linear model when we have uh, non-linearity or non-linear relation our data set have between the independent variables and dependent variable. We should implement non-linear model instead of linear model. And you have seen that as our degree of equation of model is going on increase, our model become more powerful in capturing the patterns of from the data, and it is becoming more complex model. Okay, and like in the case of last model, it has captured all the points perfectly. Okay, but although we have some flaws when we have 100% accuracy on the training data set, and what are the flaws that we usually have, we will see in the next session, which in which we you can see that we will cover underfitting and overfitting. Remember, maybe some of you have remembered that in the part of introduction, we have seen underfitting and overfitting. Just an overview, what is underfitting and overfitting. In the next session, we will see underfitting and overfitting, and I will prove you and explain you how 100% accuracy is not so good. Okay, so we will discuss it in the next session. So for now, we have learned how what is polynomial regression, why we use that polynomial regression, and how we can use that polynomial regression. So for now, thank you.